Imagine, if you will, taking this beautifully complex object, like let's just say a priceless, intricately painted ceramic vase.
Okay, I'm picturing it.
Right. Now I want you to take a hammer to it.
Oh, wow. Right.
Yeah, just smash it into a dozen scattered pieces all across the floor. Your task, obviously, is to glue it back together. But there's a catch to this puzzle, and it's a seemingly impossible one.
I feel like there's always a catch.
There is. So, the order in which you pick up those pieces determines whether the vase is perfectly restored or whether it simply like crumbles to dust in your hands.
Wait, really? Just the order?
Exactly, just the order. If you happen to pick up, say, piece A and then piece B, the glue holds flawlessly. But if you reverse that, if you pick up piece B and then piece A, the chemical reaction of the glue shatters the ceramic entirely. You just lose the vase forever.
I mean, it sounds like a riddle designed to be unsolvable, or maybe the plot device of a fantasy novel or something.
Right.
Because the idea that the sequence of an action, not the action itself, mind you, but merely the order in which you perform it, could fundamentally alter the physical reality of the object is deeply counterintuitive.
It really goes against everything we're taught.
It does.
Right.
We're conditioned to believe that the sum of the parts equals the whole, regardless of how you stack them. 2 plus 3 is 5, 3 plus 2 is 5. But what makes this scenario so compelling is that it plays out millions of times a second, completely invisibly, inside the devices you and I use every single day.
And that invisible reality is exactly what we're exploring in today's deep dive. Welcome, everyone. We are looking at a highly technical, profoundly fascinating set of notes and data from a 2026 presentation.
Yeah, it's a really unique source today.
It was put together by a developer who goes by the handle at Look036. And this presentation details the inner workings of a C++ software library called GingerClap.
Which is an open source library, right?
Exactly. The formal title of the document is Numerical Stability and Performance in Polynomial Reconstruction. Now, I can already hear some of you reaching for the pause button.
Yeah, please don't.
You hear the words polynomial reconstruction and C++ library, and your eyes might just start to glaze over. But I promise you, stick with us.
Please do. Because our mission today isn't to just read a dense computer science manual at you. That would be terrible.
Truly terrible.
Our goal is to translate this highly mathematical document into an accessible and honestly mind-bending exploration of how modern algorithms actually function. We're going to strip away the jargon and look at how machines handle numbers at a microscopic level.
A really microscopic level.
Yeah. We'll see how tiny, seemingly insignificant changes to the sequence of a task can speed up computation by massive, almost unbelievable margins, or, conversely, cause an entire system to completely collapse.
Which brings up a good point. If you aren't a programmer or, like, a mathematician, you might naturally wonder why you should care about how a specialized software library handles math. Like, why are we dedicating a deep dive to this?
Right. What's the hook for the everyday person?
Exactly. And the reason is that this presentation serves as a masterclass in problem solving. The challenges this developer faced and the solutions they engineered, they apply to so much more than just lines of code on a screen.
It demonstrates something fundamental about human intuition, and specifically, where our intuition leads us astray.
Oh, absolutely.
It shows us how naive human logic our very natural tendency to space things out evenly or to tackle tasks in a simple sequential order often fails spectacularly when applied to complex dynamic systems.
We want things to be neat and tidy.
We really do.
Yeah.
But it reveals how the architecture of task ordering can fundamentally change performance. It's a powerful lesson in why the most obvious, orderly approach is sometimes the most destructive one you could possibly choose.
So, to get into that, I want to start with the Humpty Dumpty problem of polynomials. The presentation kicks off by introducing what the developer calls the reconstruction problem.
Okay.
To set the stage, let's just imagine you have a list of roots. These are just numbers. For the sake of tracking them, we can call them R1, R2, all the way up to however many you have. Let's say Rn.
Just a big pile of numbers.
Right. And you've somehow found these roots using a root finding algorithm. Now, you need to take those individual roots and rebuild the original full polynomial equation from them.
You're trying to work backward.
Exactly. You're aiming for a target equation that looks like a standard polynomial string, coefficients attached to decreasing powers of x.
To ground that in a bit of context, think back to algebra class. When you work with a polynomial, you can often break it down into a factorized form.
Like the parentheses stuff?
Yeah, visually, it looks like a string of parentheses multiplied together. You have x minus your first root, close parentheses, multiplied by x minus your second root, and so forth.
Right.
So reconstructing the polynomial simply means taking that neatly factorized form and multiplying it all back out. You're expanding the parentheses to get the standard long equation.
And the developer's notes walk through the exact mathematical reality of how a computer executes this expansion. It relies on a process known as a convolution algorithm.
Convolution, yeah.
Instead of reading the raw formula from the slide, which is, frankly, dense with subscripts and variables, let's visualize it. The computer doesn't just instantly expand everything in one magic step.
No, it has to do the work.
It starts with a blank slate, essentially an array containing just the number 1. Then it uses a sliding window technique. It takes a current list of coefficients it's built so far and systematically weaves in the next root, multiplying and subtracting down the line to generate a new, slightly longer list of coefficients.
It's an iterative layering process. You update the coefficient list by taking each old number and combining it with the new root and the number next to it.
Step by step.
Exactly. You do this sliding calculation for every single root in your list. Eventually, you end up with what mathematicians call a monic polynomial.
Which means what exactly?
It just means the leading coefficient. So the number attached to the absolute highest power of x is just a 1. Finally, you scale the entire massive equation by whatever your original leading coefficient was actually supposed to be.
Okay, that makes sense.
Mathematically, it's a perfectly sound, deterministic process.
And it sounds so beautifully tidy, right? You multiply, you subtract, you slide the window, you repeat. But this is where the presentation introduces the central villain of this entire mathematical process.
The villain of the deep dive.
Yeah. The notes use a term that sounds incredibly dramatic for a math paper. They call it catastrophic cancellation.
It is a dramatic phrase.
No.
But I assure you, in the realm of numerical computing, it's entirely accurate.
Catastrophic, really?
Yes. Catastrophic cancellation is the moment when the computer literally loses its grip on numerical reality. It's a point where the math stops making sense and the machine starts generating pure noise.
I struggle a bit with how that happens conceptually, because from a human perspective, math is a universal truth. 2 plus 2 is 4.
Right.
If you take a list of numbers and you multiply and subtract them according to a strict formula, the result should just be the result. How does a computer experience a catastrophic failure just by doing basic arithmetic?
To understand that, we have to look at the fundamental difference between pure mathematics on a theoretical chalkboard and applied mathematics inside a physical microchip.
Okay.
On a chalkboard, numbers possess infinite precision. If you want to write out a number with 1,000,000 decimal places,
Yeah.
you just need a big enough chalkboard and enough chalk.
Sure.
But inside a computer, you are constrained by the physical hardware. Numbers are stored in a format called floating point, which you can basically think of as a highly constrained version of scientific notation.
Meaning the computer has like a set limit on how much space it can dedicate to remembering any single number?
Exactly. A standard 64-bit floating point number, which is very common in these kinds of calculations, allocates a specific number of binary bits to store the core digits. That's called the mantissa.
The mantissa. Got
And
it.
then it uses a few more bits to store the exponent, which tells you how big or small the number is. It's a finite container. There's a hard wall. Now let's look back at that convolution process we were just discussing.
A sliding window.
Right. As the computer weaves those roots together, it's generating intermediate coefficients along the way. If you aren't incredibly careful about the order in which you weave those roots, those intermediate numbers can grow to become astronomically large.
And when they get astronomically large, what happens to the tiny details? Let me try an analogy here because I think the concept of limited memory space is crucial for people to grasp.
Let's hear it.
Let's imagine you're an astronomer and you're trying to study two things simultaneously through a single fixed lens telescope. You're trying to observe a microscopic speck of dust on the lens itself. And simultaneously, you're trying to observe a massive blazing galaxy millions of light years away. The telescope has a limited dynamic range.
That's a great setup.
So if you adjust the exposure to capture the blinding light of the entire galaxy, the tiny speck of dust is completely blown out. It just vanishes. The cameras simply cannot record the massive scale and the microscopic detail at the exact same time.
That is a perfect visualization. When those intermediate numbers in the convolution process explode in size, the floating point system has to adjust its exposure, to use your word. It shifts its internal scientific notation to accommodate the massive scale of the new numbers.
Because it only has so many bits.
Right. And in doing so, it simply drops the precision of the smaller, finer details. It pushes them right off the edge of its physical memory capacity. It literally runs out of bits to track the subtle decimal level differences.
So the small numbers are they're just deleted.
They're gone, vanished.
Yeah.
But the algorithm doesn't stop.
It keeps going.
Oh yeah, it continues to the next step of the convolution, which often involves subtracting one massive intermediate number from another massive intermediate number with the mathematical goal of shrinking the coefficient back down to its final, correct, smaller size.
Oh no.
But here's the tragedy. When it performs that subtraction, the microscopic details that were supposed to dictate the final, subtle answer were already deleted in the previous step.
Because of the exposure shift.
Exactly. You subtract the massive chunks, and you're left with nothing but the empty, discarded bits. The computer essentially hallucinates the remainder.
It hallucinates. Wow. The data loss is permanent and the final answer is just corrupted.
Completely corrupted. The computer cannot successfully reconstruct our metaphorical vase because it threw away the microscopic defining edges of the ceramic pieces just so it could hold on to the larger, heavier chunks during the sorting process.
That's wild.
The pure math says the final coefficient should be something incredibly precise, like 0.0001. But the computer spits out 12 or -50 or just a string of chaotic digits because it lost the thread of the calculation entirely.
Let's dig into the origin of this error a bit more. Does the mathematical formula inherently dictate this failure? Like, is the convolution sliding window inherently flawed as a concept?
Not at all. The algorithm is mathematically flawless in an abstract universe of infinite precision.
So it's purely a physical limitation. It's the silicon itself crying out for mercy because it just doesn't have enough transistors to hold the infinite chalkboard.
Precisely. The source material highlights this beautifully. The error doesn't stem from the mathematical logic. It's exposed by the sequence of operations interacting with the hardware's strict limitations.
This leaves us with a massive problem. If we just blindly start multiplying our roots together, picking up the pieces of the vase in whatever random order they happen to be lying on the floor, the intermediate numbers explode, the telescope loses the speck of dust, catastrophic cancellation occurs, and the machine chokes.
That's the sequence of disaster. Yeah.
We have to sequence the roots to keep the math stable. We have to stop the numbers from blowing up before they have a chance to settle down. How on earth do we orchestrate that?
That challenge leads directly to the developer's solution. It's an absolutely brilliant piece of mathematical sequencing known as Leja ordering.
Leja ordering. The presentation notes describe it essentially as the art of alternating extremes. And the author of Gingercrap outlines a very specific algorithm they implemented to achieve this, which they call the greedy Leja algorithm.
The word greedy in computer science usually refers to an algorithm that makes the locally optimal choice at each step, hoping it leads to a globally optimal solution.
Kind of like taking the best immediate deal.
Right. But what's so fascinating here is how deeply counterintuitive the Leja ordering feels when you first encounter it. If you want a system to remain smooth and stable, human intuition screams at you to make small incremental changes. You ease into the water.
Right. You don't do a cannonball.
Exactly. Leja ordering does the exact opposite. It cannonballs.
The source text lays out the mechanical steps for this greedy Leja algorithm quite clearly. Step 1. You take all of your roots, every single point you need to process, and you sort them by their magnitude in ascending order.
So smallest to largest.
Right. You arrange them from the smallest absolute value to the largest absolute value. Step 2. You begin the reconstruction process with the very smallest magnitude point you have.
Okay, simple enough.
And then step 3, and this is the linchpin of the whole operation, you greedily select the next point in your list that maximizes the minimum distance to the points you have already selected.
We should really pause and dissect that phrase. Maximizing the minimum distance. It sounds a bit like a circular logic puzzle.
It totally does. The notes mention that the computational complexity of doing this is O of n squared, which the developer notes is perfectly acceptable for polynomial degrees up to 1,000.
Let's translate that big O notation for a moment. When we say an algorithm is O of n squared, we're talking about how its processing time scales as the workload increases.
The bottleneck factor.
Yeah. N is the number of items. In this case, the number of roots. If you have 10 roots, the work is roughly proportional to 10 squared, or 100 operations.
Okay.
If you double the roots to 20, the work doesn't just double. It squares. It jumps to 400 operations. So an O of n squared algorithm can become terribly slow if n gets into the millions.
Oh, I see.
But the developer is pointing out that for polynomials, which rarely have thousands of roots, the hardware can easily handle that quadratic scaling curve. The cost of running this complex sorting algorithm is negligible compared to the disaster it prevents.
That makes a lot of sense. Let's look at the visualization they provided in the text because that is what finally made maximizing the minimum distance click for me.
It's a great example.
They offer an example of roots scattered across a number line. Let's say your roots are 0.01, 0.1, 110, and 100.
So imagine that visual in your mind. A horizontal line. You have a very tiny number, 0.01, clustered way over near zero, and a very large number, 100, way out on the right edge, and a few points scattered in between.
If we execute the greedy-Lasia algorithm, step 1 is sorting them. We already did that, small to big. Step 2, we start with the absolute smallest point. So the computer locks in 0.01.
Okay, we have our first point.
Now we hit step 3. We need to look at the remaining numbers and pick the one that is the furthest possible distance away from our starting point of 0.01. That is obviously the massive number at the end of the line, 100.
Right, so your first two choices in this sequence are the absolute polar extremes of your data set. The tiny 0.01 and then the massive 100.
Now the algorithm has to pick the third number. This is where the rule applies. It has to maximize the minimum distance to the numbers it had already chosen.
This is the tricky part.
So the numbers left on the board are 0.1, 1, and 10. The distance from 10 to our chosen 100 is 90.
Right.
The distance from 10 to our chosen 0.01 is roughly 10. So the minimum distance for the number 10 to any chosen point is 10.
Because 10 is smaller than 90.
Exactly. If we evaluate the others, like 1 or 0.1, their minimum distance to a chosen point is much, much smaller because they're squished right up against 0.01.
Right, the distance from 1 to 0.01 is just under 1.
Yes. So the algorithm selects 10. It maximizes that minimum gap. Then it evaluates again and selects 0.1. Then finally, it selects 1. It progressively fills in the widest available gaps.
It forces the sequence to violently bounce back and forth between the extremes, aggressively working its way inward from the edges, systematically filling the largest available empty spaces in the distribution.
And the performance data presented in the document to justify this chaotic bouncing is simply staggering.
It's incredible.
They ran a benchmark test comparing polynomial reconstruction using these exact sample roots. When they tested the no reordering approach, meaning they just blindly multiplied the roots in whatever order they happened to be listed, the maximum coefficient error was 10 to the power of -2.
Which the developer explicitly annotates as a visible loss of data.
Visible loss.
Now, 10 to the -2 might sound small to a layperson, but in the realm of high-performance numerical computing, it's a catastrophic failure.
Like, completely unacceptable.
Exactly. It means your final answer is wrong by 100th. If this polynomial is part of a physics engine calculating the trajectory of an orbital satellite, or an engineering simulation testing the stress load on a suspension bridge, being wrong by 100th will result in the satellite burning up in the atmosphere or the bridge collapsing.
It renders the calculation physically useless.
Absolutely useless.
But then they flip the switch. They apply the greedy-Lasia ordering. They force the computer to alternate those extreme values, and the maximum error plummets from 10 to the -2 all the way down to 10 to the -14.
10 to the -14 is roughly what computer scientists refer to as machine epsilon.
Machine epsilon, let's define that. That means it's essentially flawless, correct? It is as close to absolute zero error as the physical 64-bit hardware is capable of achieving.
Yes. It represents the absolute ceiling of precision for standard double precision floating point numbers. The hardware simply cannot track a difference smaller than that.
Wow.
They took a computational process that was visibly, demonstrably failing, and without changing the mathematical formula at all, by doing nothing more than radically altering the sequence of operations, they achieved absolute mathematical perfection.
I have to pause here and push back on the underlying mechanism because my human intuition is still screaming that this shouldn't work.
I don't blame you.
Why does jumping from microscopic numbers to massive numbers magically fix the precision loss? Shouldn't violently throwing a massive multiplier like 100 into the system right after a tiny number like 0.01 create more instability?
It feels like it should.
Yeah, it feels like we're in a car and we're violently jerking the steering wheel from the far left to the far right. How does that erratic motion result in a perfectly smooth trajectory down the center of the road?
It's a brilliant question, and the answer lies in the concept of dynamic range that we touched on with the telescope analogy earlier.
Okay.
Remember how the sliding window of convolution works? You're constantly multiplying the old coefficients by the new roots. If you multiply all the large roots together first, say, you multiply by 10 and then immediately by 100, your intermediate coefficients explode instantly. You get 1,000, then maybe you hit another large root and it balloons to 100,000. The numbers race toward the edge of the floating point memory limit.
And the telescope loses the speck of dust.
Exactly. But by deliberately multiplying well-separated roots, pairing a large magnitude root with a small magnitude root, you are actively counteracting that runaway growth. You multiply the current number by 100 and the coefficient swells. But the very next step, the algorithm forces you to multiply by 0.01. The coefficient instantly shrinks back down.
You're building a governor into the engine.
You are. You're preventing the intermediate polynomial coefficients from ever blowing up to the point where they drop data. You force them to stay within a safe, moderate range before they eventually settle into their final correct values. The dynamic range of the entire operation remains perfectly balanced.
It's like applying a constant calculated counterbalance to every single extreme movement. You never let the pendulum swing too far in one direction.
That is the core of it. And if we connect this to the broader history of mathematics, the developer astutely points out in their notes that Legia ordering and polynomial reconstruction isn't an isolated trick.
It's not.
No, it's mathematically equivalent to a very famous concept called pivoting in Gaussian elimination.
Gaussian elimination. I remember the name from linear algebra, but how does it connect here?
Well, Gaussian elimination is a foundational algorithm used for solving massive systems of linear equations. It involves manipulating rows of numbers. If you just naively solve those equations from the top row to the bottom row, you can encounter the exact same floating point explosion if the algorithm happens to force a division by a very small number.
The telescope problem again.
Exactly. The intermediate values explode and the math fails. Pivoting is a technique where you preemptively rearrange the rows of your equations before you even start solving them.
Oh, clever.
You actively scan for the largest numbers and put them in the critical structural positions to keep the entire matrix stable. Legia ordering is performing the exact same structural reinforcement, just applied to the roots of a polynomial. Rearranging the inputs prevents the architectural collapse of the calculation.
So through the sheer brilliance of Legia ordering, we have officially solved the Humpty Dumpty problem. We now know how to glue the pieces of our mathematical vase back together without shattering them.
The vase is safe.
Yes, we can successfully rebuild a massive polynomial from a pile of scattered roots. But this elegant solution immediately raises a much larger structural question. How do the algorithms guess where those roots are scattered in the first place?
That is the big question.
Right. If we need the roots to build the polynomial, how does a computer locate them when all we give it is the finished polynomial?
That is the second massive challenge that the GingerQuip library has to conquer. And to understand how it hunts down these invisible roots, we have to transition our minds from the algebraic structure of polynomials to the pure geometry of circles.
The shape of a circle. The source material spends a significant amount of time detailing two highly specific root-finding methods that are implemented within the library: the Aberth method and the Bairstow method.
Let's define the distinct roles of those two algorithms based on the developer's text. The Aberth method, which is often referred to in literature as Aberth-Ehrlich, is a highly robust, generalized algorithm.
Okay.
It's designed to hunt down complex roots, and its defining feature is that it attempts to find all the roots of a polynomial simultaneously.
All at once.
Right. The Bairstow method operates a bit differently. It's specialized. It's used specifically to find real quadratic factors for even degree polynomials. It hunts for pairs rather than individuals.
So they have different targets, but the text makes it very clear that they share one massive foundational commonality. Both of these advanced root-finding methods are entirely dependent on initial guesses.
Right, they can't just know the answer.
Exactly. The computer cannot just magically look at an equation and deduce the roots. It has to seed the search space with a set of hypothetical starting points and then iteratively refine those points, pulling them closer and closer to the true answers over time.
Like zeroing in on a target.
And the geometric mechanism it uses to generate these initial guesses is to place them along the circumference of a circle mapped out in the complex plane.
So I want you to mentally draw a large circle on a blank sheet of paper. The exact center of that circle, the origin point, 0. The algorithm's very first task is to place tiny dots on the edge of that circle. Those dots are its opening bets, its initial guesses.
And the document starkly contrasts two radically different philosophies for placing those dots. The first philosophy is what the developer explicitly labels the naive approach. This is the equidistant approach.
Which is, frankly, exactly what human intuition would blindly suggest. If a manager tells you to place 8 chairs around a circular table, you don't bunch them up.
You spread them out.
You divide the 360 degrees of the table by 8, and you space them perfectly evenly.
Exactly like slicing a pizza into identical slices. The presentation notes even provide the exact angles a computer would calculate for a degree 8 polynomial using this naive equidistant method.
What are they?
The guesses are placed at 22 degrees, 56 degrees, 101 degrees, 146 degrees, and so on, marching sequentially and perfectly around the perimeter. It is the definition of orderly.
But as we just proved with the chaos of Lejeune ordering, perfectly orderly and sequential is very often the enemy of complex algorithmic stability.
Which introduces the second philosophy and the true hero of this segment, LDS. That acronym stands for Low Discrepancy Sequence. And statistically, the Gingercrap library utilizes a variation known as the van der Korpet base 2 sequence.
This sequence is where the pure math becomes incredibly elegant.
Oh, it really does.
The van der Korpet sequence completely and utterly abandons the human desire to move sequentially around the circle. Instead of taking neat, even steps from 22 degrees to 56 to 101, it employs a mechanism called binary reflection.
Okay, we need to pause and deeply unpack that. Binary reflection. I hear the term, and the notes show the resulting fractions 0.5, 0.25, 0.75. But how does the machine actually generate those numbers? What is reflecting?
It's a beautiful mechanical trick. Think about how we count in standard integers. 1, 2, 3, 4.
Simple enough.
Now write those numbers out in base 2 binary. The number 1 is just a 1. The number 2 is 1, 0. The number 3 is 1, 1. The number 4 is 100, 0.
Okay, I'm following.
Now imagine a decimal point sitting in front of those binary numbers, and you physically flip the binary digits backward across that decimal point, like a mirror.
I see. So the binary number 10, which is our standard number 2, gets flipped across the decimal to become 0.01 in binary.
Yes, and if you convert binary 0.01 back into a standard decimal fraction, you get 1/4, 0.25.
Oh, wow.
If you take the number 3, which is 1, 1 in binary, and flip it, it becomes 0.11 in binary, convert that back, and it's 3/4, 0.75.
That's amazing.
So as you count up normally in integers, the binary reflection generates a sequence of fractions that bounce wildly between 0 and 1. Get 0.5, then 0.25, then 0.75, then 0.125, then 0.625. To translate those fractions into physical locations on our circle, the algorithm simply multiplies the fraction by a full 360 degrees.
Let's trace that out. The first fraction is 0.5. Half of 360 is 180 degrees. That's the first dot.
The second fraction is 0.25. A quarter of 360 is 90 degrees. The third is 0.75, which puts the next dot at 270 degrees.
I'm looking at the full generated list from the text for a degree 8 polynomial. The sequence of angles looks completely erratic.
It really does.
It jumps to 180 degrees, then 90 degrees, then way over to 270 degrees, then back down to 45 degrees, then 225, 135, 315, and finally settling at 22.5. It's ping-ponging across the circle.
It looks like pure chaos compared to our neatly sliced pizza. But if you actually draw those points out, you realize there is a profound underlying intelligence to the sequence. The van der Korpet sequence guarantees one critical property.
What's that?
Every single new point it generates will fall exactly into the largest remaining gap on the circle.
The largest remaining gap.
Yes. Think about the progression. The first point goes at 180 degrees. The largest gap is now the entire rest of the circle. The next point goes at 90 degrees, which perfectly splits the top half.
Right.
The next goes at 270, perfectly splitting the bottom half. The next goes at 45, which splits the brand new gap between 0 and 90. It's a progressive fill. It's a completely different geometric philosophy from just taking equidistant points and shuffling them around in a random order. It's actively seeking emptiness.
Let me test an analogy on you to see if this captures the mechanism.
Come.
Imagine you are trying to parallel park a fleet of cars on a massive, completely empty city block.
Okay, I like car analogies.
The street represents our circle, our total search space. The naive equidistant method is like the drivers arriving and parking bumper to bumper. The first car parks at the extreme north end of the block, and the second car pulls up immediately behind it, and they just sequentially fill the street down to the south end.
I can picture it. It's a traffic jam right from the start.
Exactly. But the LDS, the van der Korpet method, is completely different. The first car arrives and parks at the extreme north end. The second car arrives and drives all the way to the extreme south end.
Right, seeking the gap.
The third car parks exactly in the dead middle of the empty block. The next two cars park exactly halfway between the middle car and the ends. The drivers are continually dividing the available empty space. The result is that during the entire duration of the parking process, no two cars are ever parked near each other. They're maximizing the physical distance between themselves at every single step.
That is a phenomenal analogy. And the reason that physical distance matters so desperately for these route finding algorithms is that these cars, these initial starting dots on our circle, are not stationary.
They move.
They aren't just sitting there.
Yeah.
As the algorithm runs, they move. They begin to update their positions, slowly getting pulled by the mathematical gravity of the true routes hidden in the equation.
And if they start out parked bumper to bumper,
They collide. If they start out right next to each other, like in the naive pizza slice method, their individual gravitational pulls, mathematically speaking, interfere with one another.
like magnets getting too close.
Exactly. When the algorithm tries to calculate the trajectory to move one guess toward its true route, the sheer proximity of the neighboring guess warps the calculation.
Yeah.
It accidentally drags the neighbor along with it or violently pushes it away. The points get tangled up in each other's wake.
That sounds like a mess.
It is. By utilizing the LDS sequence to ensure they are always placed in the absolute largest available gaps, you keep them mathematically isolated. You give them the breathing room they need to find their own paths without causing a pileup.
The theory sounds breathtakingly elegant, but theories don't process data. We have to ask the hard question: does this elaborate sequence actually save the computer time?
That's the real test.
The author of Gingercrap didn't just theorize, they rigorously benchmarked this. And the experiments detailed in the source material yield some genuinely wild numerical results.
This is the moment where theoretical beauty meets the harsh, unforgiving reality of CPU cycles. Let's dig into the data.
Let's start with what the notes label experiment 1 and 2. The developers set up a head-to-head battle. They ran the LDS initial guesses against the naive initial guesses using what they call the sequential abirth path, which is also known as the Gauss-Seidel path. They tested this on polynomials of varying complexities.
We need to highlight the word sequential in that path. It reveals how the algorithm processes the points. It doesn't update all the guesses at once.
Like all at the same time.
Right, it doesn't do that. It looks at the first guess, calculates its new position, locks it in, and then uses that fresh updated information to help calculate the position of the second guess. It's a cascading chain reaction.
The baseline data for a very simple degree 4 polynomial is already compelling. When using the van der Corput LDS method to place the starting guesses, the algorithm requires exactly 4 iterations or sweeps to find all the roots.
Just 4.
Just 4. When using the naive equidistant method, it requires 6 iterations.
That's a 33% reduction in workload right out of the gate. Merely by changing the starting coordinates on the circle, the computer finishes its job a third faster.
But the developer didn't stop at a basic comparison. They ran an experiment that I consider the absolute climax of this document. It's a diagnostic test that gets to the very core of algorithmic behavior. They called it the shuffle test.
The shuffle test is a stroke of diagnostic genius. It really is.
The developer basically asked a philosophical question of the machine. They asked, does the actual order of the guesses stored in the computer's memory dictate the speed, or is it merely the geometric set of points that matters?
That's a profound question.
Meaning, if you take those mathematically perfect gap-filling LDS angles, but you feed them into the computer's sequential processor in a totally random order, does the magic hold up? So they took the perfect sequence and scrambled it.
And how did the algorithm respond to the scramble?
It choked. On a degree 8 polynomial, the pure, properly ordered LDS points took 5 iterations to resolve. The worst-case shuffled order of those exact same points took 7 iterations. That's a 29% penalty in processing time simply for handing the points to the CPU out of order. But the developer went one step further. They took the LDS points, and instead of shuffling them randomly, they sorted them by angle.
Oh, interesting.
They took the van der Corput locations but forced the computer to process them sequentially around the circle, imitating the naive method.
They took the perfectly spaced cars, but forced the parking attendant to process their paperwork sequentially from north to south.
Exactly. And the iterations spiked to 8. A massive 60% increase in computational time for a degree 8 polynomial just because the sequence was sorted.
This forces us to ask why. Why does the order in the computer's memory exert such tyrannical control over the mathematical resolution? It circles right back to the fact that the birth path updates sequentially.
The cascading chain reaction you
Now,
mentioned.
let's visualize the sequence.
Right.
When the CPU processes the points in the pure LDS order, it first calculates the 180-degree guess. It updates the position and locks it. Then, the very next thing it calculates is the 90-degree guess.
Because that's the next LDS point.
Exactly. Because 180 and 90 are physically massive distances apart on our circle, the mathematical correction applied to the 90-degree guess is almost entirely independent of whatever just happened at 180. The gravitational wake at the first point hasn't reached the second point yet.
They're too far apart to mess with each other.
Exactly. The early corrections are highly stable. They don't step on each other's toes.
But if they are processed sequentially by angle,
Then the CPU updates the 22-degree guess, and immediately afterward, it calculates the 56-degree guess right next door. But the landscape just changed. The 22-degree point just moved, altering the local mathematical gravity.
Oh, man.
When the CPU tries to correct the 56-degree point, it gets shoved off target by the wake of its neighbor. The algorithm enters a vicious cycle where it has to waste precious processing cycles, constantly recorrecting points that keep bumping into each other. You mentioned marbles earlier. Or wait, maybe that was another analogy. But it's like trying to settle a bowl of marbles by vibrating it. If you vibrate marbles right next to each other, they just constantly knock each other out of place.
That physical interference explains why the data from Experiment 4 is so terrifying. The developer charted the large polynomial scaling effect, because if you're only dealing with a degree 4 or degree 8 polynomial, there just aren't that many roots in the bowl. They eventually settle down regardless of the sequence. It might take 60% longer, but going from 5 iterations to 8 iterations is still measured in milliseconds.
But a world-class software library like GingerCrop isn't built for degree 8. It's built to handle massive scale.
And scale is the exact moment the naive sequence utterly collapses. The presentation shows the benchmark data for the Bairstow root finding method running on a degree 20 polynomial.
Degree 20. So the algorithm is hunting for 20 distinct roots, or, more accurately for Bairstow, 10 quadratic factors. The search space is crowded.
When they feed the algorithm the perfectly interleaved gap-seeking LDS order, it takes exactly 4 iterations, 4 sweeps across the data to lock onto the correct answers.
Fast and clean.
Then they take those exact same starting coordinates, apply the worst-case scrambled sequence, and hit run. The algorithm grinds for 213 iterations.
213 from 4.
The impact is breathtaking. It's a 98% drop in performance. A single poorly ordered sequence is more than 50 times slower than the deliberately interleaved LDS order.
We have to contextualize that 98% slowdown. If this library is integrated into a real-time signal processing application for a cell tower or a physics engine rendering a complex fluid simulation for a video game, processing thousands of these polynomials every second, that 98% drop is catastrophic.
Yeah, the whole system freezes.
It's the difference between a program running flawlessly at 60 frames per second and a program that completely crashes the entire operating system.
It is the Humpty Dumpty vase problem playing out on a massive structural scale. All the necessary pieces of data are present in the machine's memory, but because you fed them to the processor in the wrong sequence, the cascading interference causes the entire system to crumble under its own weight.
And it definitively proves the core thesis of the developer's architecture.
Yeah.
The LDS order isn't just about picking good spots on a circle. The sequence must be interleaved.
It has to be.
The points that are physically furthest apart must be processed back to back. The efficiency of the algorithm is entirely beholden to the geometry of how the points are fed into the sequential machinery.
We've clearly established that initial guesses dictate success, and that interference in large, crowded polynomials is the enemy. But as I read further into the GingerCrypt documentation, I discovered they implemented an entirely different concept for handling a very specific subset of problems.
Oh, this part is fascinating.
It's a mathematical shortcut that acts almost like a cheat code for the algorithm.
You're referring to the implementation for palindromic polynomials, which the notes also refer to as autocorrelation polynomials.
Yes. Now, I know what a palindrome is in English. The word race car or kayak, it reads the exact same forwards and backwards. But how does a mathematical equation behave like a palindrome?
The notes define it by looking at the coefficients, the numbers attached to the x variables. The structural property is that the sequence of those coefficients reads identically from left to right as it does from right to left.
Wait, really? Like a mirror?
Exactly. The formal algebraic definition provided is p of x equals x to the power of n multiplied by p of 1 over x. But practically speaking, if your polynomial has coefficients, say A0, A1, A2, the numerical sequence might look like 3, 7, 10, 7, 3. The equation is perfectly symmetrical around its center point.
Okay, so it has structural symmetry, but why does the algorithm care if the numbers look aesthetically symmetrical? Does it change the math?
Oh, it changes everything. That structural symmetry creates a phenomenal mathematical quirk regarding the roots hiding inside the equation. If a polynomial is palindromic, the laws of algebra guarantee that if a specific number r is a root, its mathematical reciprocal 1 over r is also guaranteed to be a root.
Oh, wow. So if the algorithm discovers that the number 2 is a root, it instantly knows without doing any further calculation that 1 over 2 and 1/2 is also a root.
Right.
If 5 is a root, 1/5 is automatically a root.
Exactly. The source material notes that the roots always come in reciprocal pairs. I like to think of it as finding a buy one, get one free coupon hidden deep inside the architecture of the math.
That's a great way to put it. And the developer of this library was clever enough to realize the immense computational efficiency you can extract from that coupon because it drastically alters the workload.
The reduction in workload is massive. If the system knows for a fact that every root it finds has a mirror image reciprocal hiding somewhere else, it doesn't need to search the entire circular search space anymore.
It just cuts it in half.
Exactly. For the Abirth method, which traditionally hunts for all n roots, the algorithm can be specially configured to only look for n divided by 2 roots. You search for half of them, and you deduce the other half instantly. You've just slashed the required CPU cycles by 50%.
But the notes highlight that for the Bairstow method, the shortcut is even wilder.
Right, because we established earlier that Bairstow is specialized. It doesn't hunt for individual roots, it hunts for quadratic factors, and each of those factors contains 2 roots.
Yeah.
So a standard Bairstow algorithm needs to locate n divided by 2 quadratic factors to reconstruct all n roots. But an autocorrelation Bairstow, leveraging the reciprocal symmetry, only needs to find n divided by 4 factors.
Let me trace the math from the presentation slide to make sure I'm fully grasping the scale of this cheat code. The algorithm searches for and finds n divided by 4 factors.
Yeah.
It multiplies that number by 2 because there are 2 internal roots per quadratic factor. That calculation yields n divided by 2 roots. Then it flips the reciprocal switch, multiplying the total by 2 again to generate the mirror images.
There you go.
And boom, the machine has successfully mapped all n total roots while only executing a quarter of the initial search operations.
It's a brilliantly engineered efficiency. But, as the developer discovered, implementing that efficiency fundamentally alters the dynamic environment of the root finding process. And this brings us crashing right back into our discussion about the van der Korpit sequence and those initial guesses.
Yes, because the source material includes a highly specific data point regarding this in experiment 3. The developer tested the standard unmodified Bairstow method on a massive degree 20 polynomial.
Right.
They found that there was virtually no performance difference between using the perfectly spaced LDS initial guesses and the clustered naive guesses. Both methods required an identical number of iterations to solve the equation.
Interesting.
The standard algorithm was robust enough to just chug through the interference. But when they ran the specialized autocorrelation Bairstow variant on the exact same degree, 20 polynomial, the gap between the guessing methods exploded.
It did hold up.
No. The LDS sequence delivered a massive 58% speed up. The naive, clustered guesses took 24 iterations to clear the interference, while the LDS gap-seeking guesses took only 10.
That discrepancy is deeply revealing about how the algorithms function under stress.
I need you to explain why this happens. Why does this specific mathematical shortcut, this palindromic cheat code that vastly reduces the overall workload, suddenly make the geometric quality of the initial guess so incredibly critical?
It's a bit of a paradox, isn't it?
Yeah. If the algorithm is doing 75% less searching, shouldn't it be far more forgiving of a sloppy, clustered starting position?
It's a totally logical assumption, but the reality is the exact opposite. This goes to the heart of search space density. When you trigger the autocorrelation shortcut, you are mathematically suppressing all the reciprocal pairs. You are forcing the algorithm to ignore half the data and lock onto a much smaller set of specific primary factors.
Okay, I follow.
Because there are fewer factors being calculated, those remaining factors are now mathematically responsible for a vastly larger percentage of the final polynomial structure.
Oh, I see. They carry more structural weight. They're load-bearing pillars instead of just drywall.
That's a great way to put it. The source notes specifically describe this state as creating a tighter coupling between factors. Because you've condensed the entire mathematical problem into a smaller space, the margin for error essentially vanishes. The gravitational pull we talked about earlier between adjacent points doesn't just interfere, it becomes highly destructive.
Hmm.
If you start with a bad, clumped up, naive guess, those tightly coupled, highly weighted factors violently interfere with each other's trajectories.
Because they're carrying so much weight, when they bounce off each other, they bounce off each other much harder.
Precisely. They warp the search space entirely. But if you utilize the intelligent, gap-filling architecture of the LDS sequence, that tight coupling is perfectly managed. The LDS ordering shines brilliantly here because its entire geometric philosophy is based on respecting the need for mathematical distance.
Giving them room to breathe.
Exactly. It preemptively provides the vast breathing room the autocorrelation algorithm desperately requires to resolve those incredibly heavy, tightly coupled factors without tripping over its own feet.
Okay, let's take a step back and look at the landscape we've covered so far. We have been living entirely in the abstract realm of pure math and theoretical algorithms. We've established that the greedy liege ordering saves the polynomial from catastrophic cancellation by actively balancing the extreme magnitudes. We've learned that the van der Korpet LDS sequence strategically places our starting guesses in the largest available gaps to prevent destructive physical interference. And we've seen how autocorrelation leverages geometric symmetry to slash the processor's workload by 75%. All of these mathematical theories are sound. They are rigorously tested, mathematically proven, and flawlessly logical.
Yes, but as any veteran software engineer will eagerly tell you, possessing a perfectly proven mathematical equation on a whiteboard does absolutely nothing to guarantee perfect performance when you actually try to execute it on a physical silicon microchip.
And that profound disconnect is exactly what the author of Gingercrap ran into. When they finally compiled this beautiful, mathematically optimized code and hit run, they discovered that their flawless math was not the bottleneck.
The math was fine.
The physical computer itself was choking.
That brings us to the final and arguably most fascinating major section of the presentation, from math to machine. This is where the presentation pivots from pure mathematical theory to hardcore in-the-trenches software engineering. The developer hooked their Gingercrep library up to advanced diagnostic profiling tools.
To see what was actually going on.
Right. These tools allowed them to look under the hood and see exactly, down to the millisecond, where the computer's CPU was spending its time and energy. And what they identified were 6 critical performance bottlenecks that had absolutely nothing to do with polynomial degrees, roots, or algebraic formulas.
I love this section of the notes because it vividly illustrates how the physical reality of the machine ruthlessly asserts itself over the theoretical math. Let's walk through the developer's detective work, starting with what they label Fix 1. The document titles this bottleneck ST-ABERTH standard : future.
This is a quintessential C++ architectural issue. In the initial version of the code, when the single-threaded ABERTH algorithm successfully calculated the position of a root, it didn't just hand that simple decimal number back to the main program.
What did it do?
It wrapped that result, which is just a simple tolerance number, a floating point double inside a complex deferred object called a std.async.
Now, for those who haven't spent years debugging C++ architectures, what does that actually mean? Why is wrapping a number in an object a bad thing?
std.async is an incredibly powerful tool in modern programming. It's used for concurrency, for telling the computer to run a task in the background while the main program keeps working. But that power comes with a massive overhead cost. Wrapping a simple number in an async object requires the computer to pause its calculations, interface with the computer's operating system, and request a dedicated chunk of memory on what programmers call the heap.
The heap. I've always visualized the heap like a massive, sprawling, highly bureaucratic warehouse attached to the CPU.
That's actually pretty spot on.
If a program suddenly needs a temporary box to store a piece of data, it has to stop what it's doing on the assembly line, walk all the way into the warehouse, hunt for an empty shelf, fill out the necessary OS paperwork to officially claim that shelf, place the box down, and then walk all the way back to the assembly line to resume doing math.
That is an incredibly accurate visualization.
Mm.
Now imagine the algorithm is forced to do that entire warehouse run, complete with paperwork, for every single root on every single iteration of the search cycle.
The presentation notes reveal the scale of that waste. By stripping away that complex std.async wrapper and rewriting the code to just return the raw double value directly down the assembly line, they eliminated 96,000 heap allocations in a single test run.
96,000 bureaucratic trips to the warehouse, entirely canceled. The underlying math didn't get a single fraction of a percent smarter. The program just stopped forcing the CPU to fill out unnecessary paperwork.
And the developer's second fix, Fix 2, addresses an inefficiency that is arguably even more extreme. They profiled the Bairstow method and found a massive bottleneck labeled Bairstow copies.
Copies. The bane of performance.
The diagnostic tools revealed that deep inside the inner loop of the root finding algorithm, the computer was taking the entire massive array of polynomial coefficients and copying it over and over and over again. The text explicitly states the mathematical complexity of this waste. O of n times d copies.
Think about the physical energy that requires. Imagine you're trying to write out the complex recipe for that delicate cocktail we discussed earlier.
Okay.
But every single time you add a single drop of bitters to the shaker, you force yourself to grab a blank sheet of paper and rewrite the entire multi-page recipe from scratch before you can add the next drop.
That sounds exhausting.
It is unimaginably wasteful. The CPU is spending almost all of its electrical energy mindlessly moving data from one physical sector of RAM to another, rather than actually executing the mathematical calculations.
The developer engineered a remarkably elegant solution for this. They implemented what is known as a thread local scratch buffer.
Ah, scratch buffer.
They told the program to go to the memory warehouse exactly one time, allocate a large permanent workspace, and then just reuse that exact same physical space for every subsequent calculation. The benchmark result is staggering.
What were the numbers?
For a specific stress test involving a degree 48 polynomial with 24 distinct roots running through 2,000 iterations, they took roughly 2.3 million heap allocations and reduced them to zero.
Zero allocations. They entirely eliminated the warehouse from the process. This highlights a foundational lesson in computer science. There is a stark, unforgiving difference between the theoretical complexity of an algorithm and the physical reality of memory management.
It's huge.
You could invent a brilliant, mathematically perfect algorithm, but if your code triggers millions of background memory allocations, the operating system will step in and strangle your program. The physical hardware becomes the absolute bottleneck.
It's like engineering the most aerodynamically perfect, fastest Formula One race car in the world, but the driver insists on pulling over to buy a new cup of coffee at every single mile marker. The engine is flawless, but the pit stops are utterly destroying your lap time.
Precisely. And the developer continued this hardware optimization crusade with fixes 3 and 4, which tackle a very similar overhead issue known as thread churn.
The diagnostic notes indicate that the way the functions were being called was causing the system to constantly spawn and then instantly destroy operating system threads.
Creating a new OS thread from scratch is one of the most computationally expensive things a program can ask a computer to do. It isn't just a simple trip to the warehouse. It's the equivalent of hiring a brand new employee.
Hiring an employee.
Yeah. Setting up their desk, assigning them an email address, giving them one single task to do, and then firing them the absolute millisecond they finish it, only to turn around and hire someone else a millisecond later to do the next task.
That sounds like a nightmare for human resources.
The developer eliminated this chaos by architecting a persistent thread pool. This is essentially a singleton group of dedicated worker threads that are created once when the program starts. They stay alive, standing by, simply waiting for the main program to hand them new tasks.
The developer also added several missing reserve calls to the code, which forces the program to pre-allocate the necessary vectors. Again, it's the philosophy of preparing the warehouse shelves ahead of time instead of frantically building them while the assembly line is running.
And finally, fixes 5 and 6 bring us out of the code and down to the compiler itself.
The compiler.
Right, the compiler is the software that translates the human-readable C++ code into the literal ones and zeros the processor reads. The developer added highly specific SIMD and architecture flags, specifically -m arch equals native and /arch:\avx2 to the compiler's release mode settings.
Okay, we need to translate those acronyms. What does SIMD actually mean, and what do those flags do to the physical execution of the code?
SIMD stands for single instruction, multiple data. Modern processors, the physical silicon chips, contain specialized hardware lanes that can perform the exact same mathematical operation on an array of multiple numbers simultaneously in a single clock tick, rather than processing them one by one. Think of a grocery store checkout.
Oh, good analogy.
Processing numbers sequentially is like having one cashier scan 4 items one after the other. SIMD vectorization is like having 4 cashiers simultaneously scan 1 item each in the exact same second.
It's a massive parallel throughput increase.
Huge. But here's the catch. The compiler software is inherently conservative. It will not utilize that supercharged parallel hardware unless the programmer explicitly gives it permission to do so with those specific architecture flags.
That has to be told to use it.
By adding -m arch equals native, the developer told the compiler, look at the exact physical CPU you are currently running on, identify its maximum vectorization capabilities, and automatically rewrite the math to exploit them. They unlocked the full raw power of the physical silicon. And alongside that, they updated the library to a modern benchmark API, ensuring that their testing apparatus was actually capable of measuring this blistering new speed accurately.
You know, what I find so deeply satisfying about this entire presentation is the ultimate beautiful synergy between the abstract mathematics and the concrete software engineering. If you look at the architecture of the code base, it perfectly mirrors the math it's trying to execute.
It does. The document actually includes a visual architecture diagram toward the end, and the developer attached a brilliant definitive statement to it. They wrote, all roads lead to polyform roots with Leja ordering.
It's the ultimate safety net. It doesn't matter if the program is using the abirth method to hunt for complex roots, or the Bairstow method to locate real quadratic factors, or leveraging the autocorrelation cheat code to slice the workload of a palindromic array. All of those wildly complex, highly specialized algorithms eventually funnel their hard-won data right back down into that central function.
Right into the Leja ordering.
Exactly. The entire software library, which the notes mentioned was rigorously stress-tested against 71 highly specific edge cases and 376 distinct mathematical assertions, is purposefully built to take all of this chaotic, wildly fluctuating floating point math and land it safely in the arms of that O of n squared algorithm. It relies entirely on that algorithm to carefully, methodically alternate the extreme values to guarantee the polynomial is rebuilt without catastrophic cancellation.
It's a profound testament to robust defensive software design. You identify the single most fragile, volatile point of the entire system, the moment of polynomial reconstruction, and you build an unbreakable, mathematically proven guardrail around it.
Let's take a deep breath and recap the incredible intellectual journey this developer's notes just took us on.
We covered a tremendous amount of ground today. We really did.
We started by looking into the sheer physical danger of executing mathematical calculations inside a constrained machine. We explored catastrophic cancellation, visualizing how intermediate numbers can explode and push the microscopic details right off the edge of the floating point memory, permanently deleting the data.
And telescope analogy.
We watched the developer fix that inherent flaw with the greedy Leja algorithm, proving that violently bouncing between extreme magnitudes actively balances the dynamic range and saves the equation.
Then we shifted gears and dove into how the machine hunts for the roots in the first place. We discovered that our naive, perfectly spaced human guesses cause massive mathematical traffic jams.
The bumper-to-bumper parking.
Exactly. We solved that interference with the van der Korpet low discrepancy sequence, utilizing binary reflection to jump wildly around the circle, perpetually filling the largest gaps to keep the points mathematically isolated. We saw the undeniable proof of this when a simple shuffle of that exact sequence caused a devastating 98% slowdown on a degree 20 polynomial.
We explored how palindromic polynomials offer a massive computational shortcut by pairing roots with their mirror image reciprocals, and how that tighter coupling makes the gap-seeking LDS initial guesses absolutely vital for success.
Right.
And finally, we watched the developer transition into a hardware engineer, optimizing the C++ memory management, eliminating millions of bureaucratic heap allocations, and unlocking parallel SIMD processing, ensuring that the physical CPU wouldn't trip over its own shoelaces while trying to execute this brilliant math.
It is a wonderfully comprehensive look at exactly what it takes to build a truly robust, highly performant computational tool. And the presentation also points out that the work isn't done. The developer lays out a roadmap for the future of Gingerkate.
Right. The document mentions concrete plans for pushing the boundaries even further. They're aiming to handle massively higher degree polynomials, specifically scenarios where n is greater than 100. It talks about implementing adaptive Leja via divide and conquer strategies and advanced iterative refinement. The journey toward perfect mathematical optimization inside a machine never really ends.
It doesn't. It just continually scales up to the next plateau of complexity.
As we wrap up this deep dive, I want to step away from the code for a moment and address you directly. That's you listening to this right now. We've spent the last hour dissecting abstract algebra, floating point hardware limitations, and C++ memory allocations. But there is a deep philosophical core to this 2026 presentation that I cannot stop thinking about, and it centers entirely on the geometry of that van der Korpit sequence.
The underlying philosophy of seeking the largest gap.
Exactly. The rigorous mathematics and the benchmark data absolutely prove that starting with equally spaced, naive guesses, just slicing the pie into perfectly even pieces, or parking the cars bumper to bumper creates catastrophic interference. When things are too uniform, too tightly packed, and too rigidly sequential, they inevitably collide.
They step on each other's toes.
Their proximity causes them to fight for the exact same space, dragging the efficiency of the entire system down by 98%. The only way the developer could achieve perfect, frictionless harmony was to force the algorithm to step back, look at the entire circle, deliberately locate the single largest, emptiest gap, and place the next point exactly in the middle of it.
They maximize the distance to minimize the interference.
Right, and it forces me to ask a question that extends far beyond computer science. If this fundamental mathematical truth governs computational physics and absolute algorithmic efficiency, where else in our daily lives are we blindly making the naive mistake?
That's a great question.
How often do we schedule our time in rigid, back to back, equidistant 30-minute blocks, and then wonder why our stress levels compound and interfere with our productivity? How often do we design our cities or architect our workflows or curate the way we consume information, blindly forcing complex things into a tightly packed bumper to bumper sequence? What would happen if, instead of just mechanically stacking the next task directly on top of the last one, we paused, stepped back to view the whole circle, and actively sought out the largest remaining gaps to find our balance? Maybe, just maybe, we wouldn't shatter the vase quite so often.